Okay. Hey, 我想我可能会开始咯。OK，下一位日本的老师是2点开始嘛，对不对？那我最好是1点50分就做完，那就有 transition time, right? Okay, all right, OK， 所以我的课就是说，我不应该用中文讲。Sorry, my class is talking about the viscoelasticity, right? Right? Okay, and actually that's better. Yeah. If I can use Japanese, even easier, right? How many of you can understand Japanese? Oh, can you? Great. Okay, then let's change into Japanese, right? Then you can have 2 credit, right? Japanese and make strength of material. Why not? Okay, so the big picture is, okay, our soft robot should be made of polymer. And why that's important? Because here is a picture. Okay, polymer is the just right, will give us the just right friction. Okay, polymer is viscoelastic body like this. Okay, and as I said in the morning, any smooth surface, if you use the microscope to look at it, you can see some up and down. All right. Okay. So if your layer, friction layer, is viscous fluid, which is not possible, but let's say our caterpillar is like honey, made of honey, then you can pour honey into this space. Good. And you will stick to it really nicely. Okay, but the problem is it will stick nicely, but you cannot remove it, right? Because our robot cannot glue onto one place. It has to move on to next step, next place. So sticking onto this random shaped surface is not a good idea. So viscous fluid is not great. On the other hand, elastic body, like a soft sponge ball, if you push hard, it will attach to the random surface like this, and there will be a certain amount of contact surface area, and that will create a friction. So that is not that bad, but this will not give us enough friction. Okay, so the best middle ground is this plus this will create the polymer. Okay, then polymer will, which is a viscoelastic body, has certain viscosity, elasticity, so that it will touch the random surface like this. Okay, it will glue onto it, but when we need to remove it, okay, it can detach easily. Good. So that's why our polymer that we are going to use it for creating the soft robot is viscoelastic body. And that's why I'm sort of tasked to explain what is the viscoelasticity. Okay, it has the viscosity element and elastic element. Okay, and the elastic element is discussed used in the class of strengths of material. So most of you know already, and which I reviewed it. Okay, and by the way, I fixed a couple of locations in my slide, and I uploaded onto the Zoom. So I hope you can download it and take a look. Okay, the part I fixed was, here we go. Okay, about the homework, right? Here, this part. Okay, I said this is a hinge. This is the edge. There will be the friction and normal force, but looks like there is a gap here. Okay, and in the previous slide, I didn't state clearly, we can ignore this distance. So you can assume this point hinge and edge is exactly same location. Good? All right, so hinge to this edge is length L, edge to edge is length L, same location. Good? That's the part I didn't specify clearly in the previous class notes. Okay. And what else I changed? I changed the volume, right? Okay. All right. I talked about the volume change of the elastic body before and after the stretch. Okay. Most material still, okay, all of them change the volume. Okay. However, polymer is like a water in a Ziploc bag, plastic bag. So if you stretch it, okay, polymer, rubber, sometimes called elastomer, and biological tissues, all of them are hyperelastic, called hyperelastic material. That means before and after volume does not change, almost does not change. In the reality, it changes just a little bit. But when we are doing the macroscopic analysis, we can say polymer is like this. Okay, volume doesn't change. Good. All right. Then we talked a lot, right? A lot about the strengths of material, how strains are measured. Okay. All right. And the testing used to measure the normal stress and normal strain. Okay. And we can get the stress-strain relationship. Why we do this? Most of the time, we are only interested in this small segment of the elastic region, which usually you can find out the stress, a strain line, straight linear line between stress and strain, and slope of that part is called stiffness, okay? And it's just a small part, but by knowing after doing this testing, measuring this slope, stiffness, then you can differentiate this is a stiffer material, softer material, right? If the slope is very steep, then that's a very stiff material. The slope is not so steep, can be considered as a softer material. Good. That's the whole idea of this stress-strain relationship and the whole purpose of doing this stretch test. Good. All right. And I also mentioned, and when the elastic material are stretched or compressed, okay, along with the elongation or compression, the side dimension will change. If you have an elongation, side dimension will shrink. If you compress it, it will elongate or get wider. Good. So the ratio between this axial longitudinal strain and lateral or transverse direction strain is called Poissons ratio. Always strains lateral direction, horizontal direction, divided by strain in longitudinal or axial direction. This minus is sitting here to make sure this Poissons ratio is always positive. Good. All right, and using that one, and also applying the volume analysis before and after deformation. Okay, again, ignoring the higher order strains, second order, third order, the original volume and after deformation volume can be simplified this way using this simple formulation as a starting point. If you have a material like polymer or biological tissues, which is hyperelastic, no volume change happens before and after, then in that case, this equation says that kind of material Poissons ratio is one extreme, that is 1/2. Okay, Poissons ratio never goes above 0.5. Other extreme is that the material through the will never shrink in lateral direction. Poissons ratio is 0. Okay, I personally cannot think of any example. Okay, maybe dough. Okay, dough maybe closer, but still shrinks a little bit. So honestly speaking, I personally never seen this kind of example. Elongation does not cause any shrinkage. Okay, but theoretically we can come up with this idea. So Poissons ratio, theoretically speaking, can sit somewhere between 0.0 and 0.5. Most material is somewhere around 0.3. Okay, that means volume change a little bit. Good. Okay, and if you want to measure the stress-strain relationship for the torsion, then you have to set up this kind of tester, apply torque. One side is fixed, one side is torqued. Then gradually this end will be twisted. You can measure the angle change from those information. You can evaluate the so-called shear modulus G. Good? Okay. Again, using measured G, you can compare this material is stiffer or softer, okay, with respect to shear, right? And similarly, after doing those testing, okay, torsion testing, you can also get similar stress-strain relationship. In this case, we have shear stress, shear strain. Shear strain is basically the angle change of the small element. Good. And for isotropic material, like a tofu or steel, okay, the shear modulus G and the Young's modulus E. E is the stiffness when you pull the sample in longitudinal direction. That is the stiffness measured for that kind of situation, okay? G and Young's modulus is related this way. And again, this is the Poissons ratio, right? Okay. All right. So that's it basically. And I also talk about how to set up 3D stress strain relationship. Okay. To achieve that goal, what we need to do is do a actual test, longitudinal test in X direction, Y direction, Z direction to measure these information. Okay. Then you can set up equations this way. Okay. This is the strain stress relationship. Okay. You can set up these 3 equations from the 3 simple longitudinal actual stretch tests applied on each material in each directions. Okay. Then also apply shear stress, shear testing. Okay, around the x-axis, y-axis, z-axis, then you can get this relationship. Okay. All right. Then finally, combining this, and these 3 equations after a couple of minutes or hours of struggle, then you should be able to set up stress strain relationship. In between is I'm using the matrix notation. Okay. Matrix is okay, everybody. I hope you have seen matrix before. Linear algebra. Good. So matrix. Okay, this is the matrix stiffness. This is the stiffness, stiffness matrix. This is stress vector, strain vector. Good. Can be expressed this way. All right. Okay. Then I talked a little bit about the Charles Lindbergh. I hope it was sort of interesting idea. Then now we are going to move on to the viscoelastic part. Okay. All right. Viscoelasticity. Here's the video of viscoelastic material. This is viscoelastic, and this is also viscoelastic. And this person is going to apply twitch. Okay. And you can see one of them goes back faster, go back to the original shape faster, the other one. Good. Okay. If both of them were elastic, after you apply twitch, let it go, it will boom, come back right away. No time delay. But as you can see here, what happened? Yeah, so as you can see, this is going back to the original shape faster. So this material is more elastic, less viscous. This is less elastic. This is more viscous. So it takes time to go back to original shape. Okay, that's the major differences between elastic and viscoelastic material. All right, so to study analyze the viscosity element of the viscoelastic property, because it's time dependent, okay? So we have to know how to analyze the time domain problem, okay? This is the not so exciting part, okay? All right, so here we go. Okay, allow me to go through the generalized way to describe the time domain response, Okay, here, oops, this is, I should knock out 1 plus here. Okay, this is the second order differential equation. Prime means this y is differentiated by time twice. This is acceleration. Okay, y prime means y differentiated by time once. So this is velocity. This you can say it's a displacement. Good. Okay, and this is a very typical equation if you're analyzing the vibration problem. Okay, sorry about this extra plus. Good. So this is second order differential equation. I hope you have seen this in engineering math, right? You took engineering math, right? Right. Okay. Good. All right. So good. So basically, so this is second order differential equation, ordinal differential equation, and here's the input part. Good. All right. Okay. So you can imagine this is vibration. So if you don't have this, solve this part, it will vibrate, give you the vibration. Good, sine, cosines, okay? However, this is the damping factor. So if you don't have this and vibrate, it will vibrate gradually, get smaller and smaller and smaller. But we have exciting forcing term here. So how can we solve this problem? Okay, let's say this is the step input, okay? Step input means you apply step. So to the system, so if you apply step input to this second order differential equation, pop. Okay, this is the forcing term, all right? However, you will see two parts. First part is the vibrational part. That part is called transient response, okay? Once this happens, this part is the dominant phenomena. So once popped, this part says, I'm going to vibrate and decay. So vibrate and decay. However, at the end of the day, this system is forced to listen to this step input. So eventually it will become unit step input 1. Okay, so the first part is the transient response that is governed by homogeneous solution. Homogeneous solution is given by setting up this equal to 0, solve that equation, that's the homogeneous solution, okay? Particular solution is the one with this, okay? So steady state part is the particular solution, transient part is the homogeneous solution. Good, not so important, but that's the terminology, all right? Okay. All right, let's solve this problem, okay? Again, it's not so important. I just want you to follow this boring part. Okay, here I have ordinal differential equations, acceleration plus displacement. I don't have velocity term. That sort of later you'll find out this system, it is going to vibrate, but vibration never decays. Okay, the forcing term is sine. That is from here, we can sort of guess at the end, this system will be forced to show this sine 2t curve. Good? All right. Okay, so how should we solve this? And to solve this problem, we need to, somebody need to provide us with the initial condition. So displacement at the t equal to 0, in this case is 2. Velocity, initial velocity is equal to 1. We need to have 2, okay? Otherwise, this problem cannot be solved. Okay, standard way to solve this is set this as a 0 and homogeneous equation and assume there is a mass here, K. And then we can grab the template, okay? Template like this, okay? All right. Then that is our solution, good, okay? And CN2, we'll worry about it later. Okay, particular solution is the one with this sine 2t, okay? So the system at the end, we know will be forced to act like this. So that means steady state at the end, we can assume this system is going to vibrate cosine 2t and sine 2t, right? To make it general, okay? At the end, you'll find out we don't need to worry about it. But assuming this, and since I don't know the contribution of cosine, this is unknown constant, and this is unknown constant. Good? Okay. right? This is a very standard way to solve it, okay? So using this one, differentiate twice, once, yada, yada, yada. Okay, now you can get this relationship. Right-hand side, we know this is the forcing term. By assuming this particular solution for steady state, we found out this left-hand side is lengthy relation like this. Okay, organizing it, you can find out one constant is here, another constant is here, right? Good? All right, and what we can say? Left-hand side says it has to be sine 2t. Sorry, right-hand side is 1 times sine 2t. Left-hand side says something times cosine 2t, something times sine 2t. So what can we say here? What's your guess? This should be equal to what? 0, right? Because I don't have any cosine 2t, so this should be 0, right? Good. Okay. And now we have sine 2t. It says 1 sine 2t, so we can say this should be 1, right? Good. All right. So set up that relationship. Okay, you can find out a is equal to 0, b is equal to that. Okay. Then finally, we set up the general solution from the homogeneous solution from the transient state, steady state solution found from here. Now I still have unknown C1 and C2, 2 unknowns, okay? But good news is, as I said, we always get 2 initial conditions, 2 equations, 2 unknowns, so we can find out those unknown C1, C2 can be found, okay? Then finally, we can say this solution is this, okay? All right, that's a very standard way to solve this, okay? But one problem is, this one is second order differential equation, so there is a template always. So we can do this easily. Good. All right. The problem is if there is no template, what should we do? Okay. What should we do? Then we can use a method called Laplace transformation. All right. The idea of the Laplace transformation is if you have some kind of time function, okay, apply exponential of power of minus st. S is the complex frequency. Good. All right. Have you seen this before? Oh, good. All right. Then you can convert into this frequency domain, right? Good. Okay. So using the Laplace transformation, we can convert. The idea is applying Laplace transformation to time domain, you can convert into whatever the frequency domain. Good. All right. Okay, here's the example why we need to do this. Okay, here, let's say we have this time domain equation. Okay, second order differential equations here looks very intimidating. Okay, annoying. But this time domain throw into the Laplace transformation. Most of the time, we don't need to even do this because there is a table, Laplace table, if you remember. So this part is just looking at the table. Then we can convert this into a simple algebra, right? Right? There is no differentiation here. Okay. Then in this space, we can find out the solution. Then we can convert back. That's the idea. Great invention done by the Laplace. Okay. That's the idea of the Laplace transformation. Okay. All right. Good. So basically, this is the original definition of the Laplace. Okay. There is a similar conversion called Fourier transformation. Have you heard of it? Okay. It's a cousin. It's pretty much same thing. Okay. All right. Fourier transformation assumes this function is sinusoidal. Laplace transformation assumes this function is not sinusoidal. Okay. That's the difference, but pretty much same thing. Okay, so here are the couple of examples. Okay, if you have a function t that is equal to 1, apply this. Okay, all right. Couple of minutes of struggle, you'll find out in time domain it will become 1 over s. Okay, all right. If you have this kind of function in time domain, again, just apply this. Okay, it's not so hard. Integration by parts and this and that, then frequency domain will look like this. Good. All right. But good news is, again, most engineer, we don't need to even do this, okay? Because I don't know who created this, but usually there's a table, okay? Table like this already existing, okay? If you have this kind of function, then frequency domain looks like this. Most of the time, that's the case. All right? Okay. So on and so forth. All right? Okay. Then once you bring everything into frequency domain or S domain, in S domain, no differentiation, solve the algebra, okay? Then you find the frequency domain answer. At the end of the day, we live in time domain, so we have to back out. So we have to apply what? From frequency domain to time domain, what do we need to do? Inverse Laplace, right? Okay, so that's it. Okay, so reverse is inverse Laplace transformation. Usually, definition looks like this. Okay, again, good news is we don't need to even do this because there is a table. All right. Okay, but sometimes the maneuver is not so straightforward. Okay, sometimes you have a time function, but you cannot find the exactly counterpart, the counterpart of the frequency domain to a time function. Okay, all right. That means your frequency domain solution, is too complex, so we have to simplify it by using the partial fraction expansion. Okay, all right. So something like this. Good. Let's say our final solution in frequency domain is found out to be like this. But if you look at the Laplace table, you can never find out the time domain counterpart to this. Good. That means this is not simple enough, so we have to further simplify this. Okay. That maneuver is called partial fraction expansion. Okay. All right. Good. So we would like to simplify it. Okay. All right. Okay. So this can be simplified this way. Okay. All right. If we can break this into something over sine plus s plus 1, s something over s plus 2, this you can find in the table. This you can find in the table. Okay. So now the problem is, how can I find out this K1 and K2? Okay. This to this true. This to this possible. Okay. The question is, how can I find out K1 and K2? If that is found, this I can go to the table to find out the time domain. I can also find out the time domain of this using the table. Good. That's the essence of the partial fraction expansion. Okay. All right. The method one, couple ways to do it. Okay. Multiply S1 to both sides. Okay. This side will become 2 over s plus 2. This side you have K1 and this. All right. Then we set s equal to -1, s equal to -1. All right, then this will become 0, right? If we set s equal to -1, this will disappears. This disappears. And the right-hand side, -1 plus 2 is 1. 2 over 1 is 2. Okay, right-hand side, K1. So using this simple sort of cheating method, K1 is found out to be 2. Okay. Similarly, using similar technique, you can find out the K2. Okay. K2 in this case is -2. Then finally, we can say this originally looked like a very intimidating fraction. Now it's simplified this way. This, if you go to the table, you can find out the counterpart in time domain. That's the idea. Good. That's the essence of partial fraction expansion. The other way to do it, okay? Well, anyway. All right, so let's apply the Laplace transformation, partial fraction expansion to this. What will happen? Okay, first apply Laplace, okay, burn everything, t change into s. Okay, this is initial condition. This is given here too. Okay, this is not frequency domain. This is time domain initial condition. So it's already given. All right, and this is what I have. Okay, then solving this, I can get this. Good. All right, great. And this one, we can find out the time domain counterpart using the table. This we can't, okay? Then it's sad, but we just need to apply partial fraction expansion, okay? Then you can simplify it, okay? Sorry, we can skip this part, okay? So in frequency domain, you can find out this. Right then, last part is each time you just need to go to the Laplace transformation table, then convert into time domain, right? Okay, this exists, so on and so forth, okay. Then finally, this is the time domain solution using the Laplace and inverse Laplace transformation. Good, all right? That is the great invention, okay? So overview is something like this, right? Okay, if you are math major, maybe you may enjoy solving solution from here to here, okay, directly, okay? But if you do not mind going through one step of Laplace transformation and converting the time domain to frequency domain, okay? All right. This part looks annoying, but fact is this is done by table, okay, pretty much done by table. Okay, so it will be simplified this way. Good. Beauty of this is everything is algebra. There is no differentiation. This is the initial condition. These are already a number. So this is very easy to solve in frequency domain. Okay, now you have a solution in frequency domain. Okay, in this process, you may need to apply partial fraction expansion to get more simplified fraction. Once that is achieved, then we need to go back out by looking at the table again, right? By looking at the table, okay, then find out the counterpart, then here's the solution. Good, that is the beauty of time domain analysis using the Laplace transformation. Okay, all right. So since the viscoelastic material has the response of the viscoelastic material is time domain, time dependent, so we will use this a lot. Okay, where am I? 20 minutes to go. Good. Okay, if you have viscoelastic material, okay, you pour it, okay, and the response stress-strain relationship depends on how fast you pour. Surprisingly enough, if you pour slowly, okay, the material will fight back less. So the reaction stress is a lot less. If you pour really fast, it will fight back more. So the reaction stress is higher, right? Okay, so it's time dependent, all right? Okay, so to find out the viscoelastic property, usually we will do two kinds of testing. One is the apply, okay, step stress input, okay, apply step input of the stress, okay, then see what will happen to the viscoelastic material. If you have elastic material does not have time delay. So as you can see, if you apply stress this way, pop, let it go, pops down, elastic material, strain will pop, stay flat, pops down. This is the response of the elastic material. Good? Okay. All right. However, okay, viscoelastic material, if you apply a step stress, it will creep up gradually. Then after you release it, it will recover gradually. Okay, it's very time dependent. All right, that is the one kind of test we can do to find out the viscoelastic property. Okay, the other one is the, okay, by the way, so this is creep and relaxation test, recovery test. This is called relaxation test. Difference is here, strain is, step strain is applied here, pop, then see what kind of stress response will be measured. If you have elastic material, stress response is no time delay, so it will pop up, stay the same. Good. However, if you have a viscoelastic material, it will go up fast, not right away. This is not right away pop up. There's a slope, goes up, overshoot, and comes down gradually. Okay. All right. Good. So these are the tests usually we apply to find out the viscoelastic element of the viscoelastic property. Good. All right. And by doing so, you can find out what kind of your material has what kind of viscosity, what kind of elasticity. Then from those things, you can figure out the friction. That's why. Okay. All right. Then one final annoying part is this test we know how to do, but at the end of the day, we need to have a mathematical model so that we can recover viscoelastic property, right? So there are a couple mathematical model proposed. Okay. All right. Viscoelastic element has two elements. One is the elastic element. Elastic element is simple. Simply, it's a Fuchs law, right? Spring here, okay? Spring, one side is glued onto the wall. If you pull the other side, free body diagram looks like this, right? Action force, reaction force, okay? And the relationship between applied force and elongation is one straight line. This slope is the spring constant, okay? No time delay between the applied force and elongation x, okay? That is the elastic element of the viscoelastic property, okay? Now, viscous element, okay? Viscous element, usually the simplest viscous element is the viscous damper, okay? Damper, inside you have a sticky fluid, there is the bar, you can pour out, okay? This kind of element usually can be modeled this way. Applied force is linearly dependent, is related to the speed of pour out. Okay, you apply force here, you cannot pour out right away. You can gradually pour out. That is a speed. Okay, so if you have a simplest element of the viscous element is viscous friction is here. Good. All right. Okay. And as you can see, this is a time function. All right. And the easiest example of viscoelastic material is the suspension damper that we use for automobile. Okay. Automobile or motorcycle, there is a spring outside to store the elastic energy. Inside is the viscous fluid. Okay, this will act as a damper. Good. All right, so the model one, okay. Model one is proposed by Kelvin and Vogt. Okay. All right, they said we can do this. We can come up with this simple viscoelastic model. In their model, elastic spring is sitting one side, viscous damper is sitting another side. Okay, they are sitting in a parallel manner. Okay, from this model, what kind of relationship we can derive? Okay, you cut here, you can get the free body diagram. Each of them is subjected to stress, spring stress, damper stress. But the fact is, these two are subjected to one sigma stress. So external applied sigma here. So clearly this is equal to this plus this, right? Okay. So using their model, okay. But what we can say is this is going to elongate in the same manner. Okay. So the strain happening in the spring, the amount of the strain happening in the damper should be exactly the same. That is the total strain total strain from here to here that can be measured from outside. Good. Based on this assumption, okay. All right, we can set up these two equations. Spring element is simple. Stress strain relationship. We also learned viscous damper has this relationship, okay? But this should be a time derivative. So we should have a strain dot. One dot means time derivative. Good. All right. And at the end, this plus this will give us the total strain, right? Stress, sorry. Right. So total stress is given by this and this. So based on this simple Kelvin-Vogt model, we can say strain and stress are related by this. Good. And again, it's not present, I can see that. But here we have a time derivative here. So that's why usually we will implement Laplace transformation to handle this problem. Okay. Okay, another one is Maxwell model. Okay, Maxwell model. The elastic spring and damper is sitting in the serial manner. Okay, one after another. You can set up the free body diagram this way. One thing, special feature about this problem is this one is subjected to spring stress. This one is subjected to damper stress, and outside is total stress. Clearly, this should be equal to damper stress. Damper stress should be equal to spring stress. Okay, by introducing those, okay, then we can say, the total strain should be spring strain plus damper strain. Okay, combining these two, we can get slightly different stress-strain relationship. This is the Maxwell model. All right. Okay. Then people try this to test the viscoelastic material, and most of the time they found out one model is good to describe one kind of phenomena, but fail to describe another kind of phenomena. So people kept coming up with more complex model. Okay, one is called standard solid. Okay, and as you can see, this is Kelvin model plus Maxwell model, basically. Okay, this will look more complex. Okay, all right. Oh, sorry. Okay. All right. And as a result, okay, this so-called standard model, you have time domain relationship will look much more complex. Okay. But the good news is if you make the model more complex, usually the possibility of fitting your measured data from your viscoelastic material or biological tissues, the possibility of fitting the data is much, much higher. Okay, so that's why people keep adding more element, and as a result, equation looks more uglier and uglier. And people says, I finally found out the best equation. That's true, but sometimes that kind of equation has too many parameters. Okay, all right. So these are the major viscoelastic models. Okay, all right. Then to find out the time domain response, okay, as I said, we have to apply the Laplace transformation. Okay, all right. Kelvin model. Okay, to find out the time domain response, okay, you have to apply Laplace transformation. Okay, and first, sigma is step input 1, so apply Laplace transformation in frequency domain will become 1 over s. All right. And then this entire relationship after applying Laplace transformation looks like this, solving this, and you can find out strain in frequency domain looks like this. And finally, we need to find out the strain response in time domain will look like this. Okay, that's the whole idea, because at the end of the day, we do the testing in time domain. Okay, then using the time domain result, we need to find out the E's or mu's. That's why. Okay, that's why we need to go through this. Okay. And Kelvin model, similarly, this way. Good. All right. I ran a simple simulation using the Matlab. Okay. But came to think about it. Maybe most of you have you ever used Matlab before? Or Python? Which one you used? Python or Matlab? Matlab. Oh, okay. Then you should more familiar to you. So Matlab has a symbolic calculator. Okay, here says in the Matlab, sims means I'm going to declare T and S is symbol, right? And Young's modulus is 1, mu is 0.5. These are the parameter. Okay, then I will this one. Okay, frequency domain strain. I found out to be this. Okay, good news is I don't need to do inverse Laplace transformation by hand myself. Okay, Matlab has a function called in symbolic toolbox has called inverse Laplace. Then it will give you the time domain step solution. Then you just need to plot this in using the symbolic calculator. Okay, usually we use plot, but if you're using the symbolic functions, this is a symbolic function, okay, then you have to use easy plot. This means plot this function from 0 to 1, okay, and in y direction is 0 to 2. That's it. Good. All right, and same thing. All right, creep test looks nice. Okay, relaxation test using the Kelvin model is not so nice. So this is what I said. Okay. All right, and the Maxwell model, here we go, similar result. Okay, all right, good. And standard model, okay, so on and so forth. Good, so basic idea is we go through this, okay, looks ridiculous, okay, but however, end of the day, what we want to do is we would like to find out the time domain response because we do the testing. The measured data is in time domain. So we need to find out the time domain response mathematical model so that we can use this to compare to the measured data to find out what is the elasticity 1, 2, viscosity mu. That's it, okay? Once those are found, then we can say what kind of viscoelastic material we have. Good? That's the big picture. Okay, all right, what time is it now? Whoa, it's 50 now. Okay, and usually what we do is first use the testing, okay, relaxation test, recovery test, okay? Then here's the data, noisy, all right? Then what we have to do is, let's say I would like to fit a Maxwell model. This is the Maxwell model. Okay, how can I fit this data into here? Okay, these are data measured already. Okay, so what we need to do is for the Maxwell model, we have exponential here. So we apply log. Okay, we apply log. Then we will have a, this is measured. This is measured. Okay, time is measured. I would like to find out what is the E mu here. Okay, apply log. Then you have a log of the measured stress. Okay, easy. Here we go. Okay, this is one parameter we don't know yet. Here's the log here. Okay, that can be further simplified. Okay, if you apply log, natural log to exponential, then you can get this. So measured, time is measured. This we can calculate. Things we need to inversely find out is log of E and this. So we can replace this as a, replace this as a B, then apply so-called regression analysis. You can find out A and B. Once you find out the A, apply log E is equal to A, you can find out the E. Once you have a E, you can find out the mu. Good. That's the way we play with the data. Okay. All right, that's it. So basically, once you do a testing, you create your viscoelastic polymer, do the testing, do this, you can find out this. Then you can tell this is a good viscoelastic property that has a good amount of elasticity, viscosity. Good? That's the whole idea. All right. Thank you so much for being patient with me. Okay, and one more, sorry, homework from today is, I want you to look for the paper, okay? All right, I think you should do the paper search here on campus. Then through the NTUST IP address, you should be able to find lots of paper, talks about the friction and viscoelasticity of the material, and describe the, summarize the paper. Good, roughly easy enough. Okay, most of them use ridiculous amount of the equations. And I know it's really hard to understand all of them, but roughly understand it, read it, then summarize it. That's good enough. Good. All right, so that is the homework from today. So I gave you 2 homework, right? Good. All right. I know it's a lot, but in America, usually professor will give you this kind of problem homework, 2 of them every day. So every day's homework is like this. Okay, it's crazy. All right, thanks so much. Okay. Oops, this is. All right.
KB